Hello everyone, and thank you all for taking the time to watch this presentation. My name is Victor Salas Moreno, and it is my absolute pleasure to present the findings of our recent research work titled Elements of Minimum Norm in Banach Spaces of Bounded Functions and an Application. This work represents a deeply rewarding multidisciplinary collaboration between the Department of Electronics and the Department of Mathematics at the University of Cádiz. Often, pure functional analysis and applied engineering operate in silos, speaking entirely different languages. However, in this presentation, we are going to explore a fundamental theoretical problem in the geometry of Banach spaces, and I will demonstrate step by step how its rigorous analytical solution perfectly resolves a highly practical physical engineering challenge in modern electronics. To provide some crucial historical context, the quest to understand norm-attaining operators and their associated supporting vectors has been foundational pillar of functional analysis since its very inception. This prolific area of research has yielded cornerstone mathematical results, such as the famous Jens theorem characterizing reflexivity, and the Bishop's-Fels theorem providing the density of norm-attaining functionals. A deeply related parallel problem and the central focus of our work today is the challenge of minimizing the norm of a vector over a specific subset of a norm space. This is intimately related to proximality and the distance from a set to the origin. But this isn't just an abstract mathematical exercise. It is a fundamental structural task in optimization theory. In fact, these exact minimization problems are absolutely critical in the real world right now. They play central, indispensable roles in the optimal designs of transcranial magnetic stimulation coils used in neurology and in magnetic resonance imaging gradient coils. In all these cases, we want to minimize physical energy or maximum current while achieving a specific electromagnetic target. Let us formalize the math behind this optimization. Consider three real norm spaces, X, Y, and Z. We also define two bounded linear operators, J and T. We start by defining problem 1, which represents the most general minimization problem. Here, we seek to minimize the norm of a composed mapping, the norm of J of X, subject to the linear constraint that T of X equals Y0. By applying a clever change of variables, this general case can be structurally reduced to what we call problem 2. This is the standard minimum norm problem, simple finding the minimum of the norm of X, subject to that exact same constraint, T of X equals Y0. Please note that problem 2 is the primary focus of our analytical development today. It strips away the unnecessary complexity. If we can solve problem 2, we essentially unlock the analytical solution to the much broader, more complex constraint optimization problems found in real-world physics. Before presenting our analytical solutions, we must recall two geometrically vital concepts. First, we define the operator norm of a bounded linear operator T. Geometrically, this is the supremum of the norm of T of X, measured over the entire closed unit ball of X. You can think of it as the maximum possible stretching factor that the operator T can apply to any vector. Second, and most crucially for our optimization, we define the set of supporting vectors of x for t. This is denoted as support V of t. These are those specific special element x in our space where the operator achieves its absolute maximum theoretical stretching. That is, the points where the norm of t of x is exactly perfectly equals the norm of t times the norm of x. Similarly, for any bounded linear functional x star residing in the dual space, its supporting vectors are those exact points of the unit sphere where the functional touches its bounding hyperplane. 0 is trivially always a supporting vector, but it is the non-zero supporting vectors that give us the explicit geometry boundaries we need to perform a strict optimization. Our methodology begins by establishing proposition 1, which serves as the theoretical bridge between our complex and simple optimization problems. The proposition states that if we can find a bounded linear operator R that acts as the left inverse to J, meaning that R composed with J gives the identity operator, and its operator norm is bounded by exactly 1, then we can map the solutions perfectly. Specifically, the solutions of a simplified optimization problem labeled here as problem 8 map directly into the solution set of our overarching general problem 1. The significance of this result is profound for applied mathematicians. It allows us to mathematically strip away the complexity of the operator J entirely. By utilizing this left inverse, we reformulate our minimization problem purely into the standard form of problem 2, but now utilizing the composed operator T composed with R. This fundamentally simplifies the topology we have to navigate. So, practically speaking, how do we find these minimum norm elements once we are in problem 2? Proposition 2 gives us a highly powerful geometric sufficiency condition. It tells us that if a vector is a supporting vector of T and it simultaneously satisfies our physical constraint T of x equals y0, then it is absolutely guaranteed to be a solution of the minimum norm problem. This powerful geometric insight leads directly to corollary 1, which completely and analytically solves the problem when we are minimizing over hyperplanes. If our target operator is simple, a linear functional x star evaluating to a scalar t0, the solutions are precisely the scaled version of its non-zero supporting vectors. This isn't just an approximation, it provides a direct, exact algebraic formula for calculating the minimum norm element in one shot. Now we arrive at the core theoretical contribution of our work. We restrict our mathematical attention specifically to the Banach space V of lambda. This is the space of real-valued bounded functions endowed with the supremum norm or the infinity norm. Here we introduce a novel mathematical concept, the transversal operator. An operator T is deemed transversal if its kernel is not entirely contained within the kernel of any single coordinate functional. In plain terms, this means that no single individual coordinate axis can strictly dictate the behavior of the operator's null space. Theorem 1 characterizes the solutions in this space perfectly, breaking them down into two distinct geometric realities. In the non-transversal case, the geometry is simple. The solution's infinity norm is strictly dictated by the absolute value of the function at that one single dominant coordinate lambda 0. But in the transversal case, the geometry becomes much more rigid. If the infinity norm is attained at any specific coordinate lambda, then peeling or subtracting that coordinate away forces the remainder of the vector to still retain that exact same maximum infinity norm. Theorem 2 takes the transversal case even further, revealing an incredible structural symmetry. Let's suppose we have an optimal solution x0 that attains its maximum infinity norm on a specific subset of coordinates, which we will call the set gamma. If we can find any perturbation vector set residing in the kernel of T that happens to share the exact same signs as x0 across all coordinates in gamma, we reach a fascinating mathematical conclusion. Subtracting the entire projection of x0 onto gamma does not decrease the infinity norm of the vector whatsoever. This theorem essentially proves that for transversal operators, the minimum norm solutions are incredibly symmetric and highly robust against local perturbations. The maximum norm is deeply embedded across multiple components, not just a fragile peak at a single point. To properly ground these abstract theorems, let's look at a concrete, simple 3D example in L infinite 3. We want to minimize the infinity norm of a 3D vector xyz subject to a simple 2 by 3 linear system representing our constraints. By parameterizing the feasible region, which is just a line in 3D space, we find that all valid vectors look like 1 minus alpha, alpha 2 minus alpha. Evaluating the infinity norm for all real values of alpha, we discover that the absolute unique minimum occurs exactly at alpha equals 1. This gives us the definite solution vector 0, 1, 1. The infinity norm of this optimal vector is exactly 1. Notice a critical detail here. The first coordinate is exactly 0. This is the crucial theoretical takeaway for applied work. In transversal operators, the minimum norm solution does not need to attain its maximum magnitude at every single component. It only attains the maximum value of 1 at the y and z coordinates. Rounding out the theoretical section of our presentation, Theorem 3 and Corollary 2 provide us with strict, uncompromising duality results. Theorem 3 explicitly defines the supporting vectors of any bounded linear functional x star on the space V of lambda. It demands a strict sign matching condition. For a vector to be a supporting vector, the mathematical signs of the function at any coordinate must exactly and perfectly match the sign of the functional's evaluation at that specific coordinate. When our set lambda is a finite set, the set inclusions you see mathematically on the slide become exact, locked equalities. This is fantastic news because it provides us with a flawed, deterministic analytical formula to compute exact minimum norm elements under functional constraints in finite-dimensional spaces. We no longer have to guess, we can calculate it directly. Now, let's transition from abstract Banach spaces and see why this pure mathematics deeply matters in the real physical world. We applied our analytical solution directly to the designs of near-field communication or NFC antennas. In standard PCB manufacturing, tightly packed antenna tracks are a nightmare. They cause unwanted capacitive coupling, signal crosstalk, and manufacturing errors that lead to short circuits. Our engineering objective was to minimize the physical spacing between the PCV tracks to prevent these issues. Physically, maximizing track spacing is mathematically identical to minimizing the maximum current density in the antenna structure. Using a magneto-quasi-static formulation, our goal is to minimize the infinite norm of the current density Jc, while simultaneously maximizing the magnetic field B sub Z at a specific target location. Through the exact change of variables we discussed earlier in proposition 1, this messy physical problem transformed perfectly and cleanly into our standard problem 2. By applying corollary 2 to our newly transformed problem, the mathematics has the exact optimal current distribution without requiring numerical approximations. The optimal current X sub j at any physical segment of the antenna is determined simply by the sign of the magnetic field sensitivity coefficient A sub j. The magnitude of the current is uniform across the board, meaning that the infinitive norm of X equals 1. Because this unique solution simultaneously minimizes the infinity norm of the current, thus spreading the tracks, while maximizing the linear combination of the magnetic field at the target. It is, by strict definition, a Pareto-optimal design. We are sacrificing absolutely nothing in signal strength to achieve perfect manufacturability. As you can see on the screen, we have successfully achieved the minimization of the maximum current density in the antenna, which directly maximizes the minimum spacing between the PCV tracks. Let us illustrate this result practically by designing an antenna of a square of 3.5 mm per side. This specific antenna is designed to generate a maximum magnetic field at a distance of exactly 0.25 mm above its center for a 0.2 mA current peak. The PCV track pattern obtained from our mathematical solution is depicted on the left in figure 1a. Here, it can be clearly seen that we achieve a maximal highly uniform spread of the PCV tracks, completely avoiding the risk of capacitive breakdown. When this antenna is energized, it produces the magnetic field map displayed on the right in figure 1b. Here, it is worth noting that the bright yellow region, the maximum value of B sub z, perfectly occurs exactly at our desired target location in the center. To conclude our presentation today, our work successfully bridges a critical gap between abstract functional analysis and highly practical electromagnetics. Mathematically, we provide a robust, rigorous characterization of minimum norm elements in Banach spaces of bounded functions, and we introduced the powerful new framework of transversal operators. Engineering-wise, we successfully translated these abstract theorems into an exact analytical optimization technique that resolves physical manufacturing constraints. Beyond NFC application, this methodology is incredibly versatile. It is directly applicable to the optimal designs of wireless power transfer coils, biomedical inductive links for implants, and sensor excitation coils, or indeed anywhere in the world where spatial magnetic selectivity and physical constraint optimization are critical. Thank you very much for your time and attention today.